Hello everyone, myself Sakshi Mittal. I welcome you all to my third lecture for topic 8086 Memory Organization for subject AKGEC 403 Microprocessor. I am Assistant Professor in Department of Electronics and Communication Engineering, AKGEC Engineering College, Ghaziabad. So in this lecture, we are going to discuss about the memory organization, segmentation part, how we can generate the physical address for 8086. First, we will start with the addressing. If we have got, what is a memory? Memory is nothing but it is a stack of locations. So how can you arrange your memory? So there can be two types of memory organizations, a linear addressing and a segmented addressing. Linear addressing says that the entire memory space is available to the processor in one linear array. However, your segmented addressing says that the all available space, it is being divided into chunks, or you can say the pieces, and we call those chunks as the segments. And so we have divided the memory space into chunks, into pieces, so we are calling it as a segmented addressing. 8085 used to have a linear addressing, but 8086 is used to have the segmented addressing. So in 8086, the available memory space is 1 megabytes. So the memory is divided into number of logical segments. But why the memory is divided? See, we have got a size of 1 megabyte. So to access 1 MB memory, you need a 20-bit address. To store a 20-bit address, you need a 20-bit register. But 8086 is having 14 16-bit registers. You do not have any register which has a storage of 20-bit. So I need something. How can I access my 20-bit my 1 MB memory with the help of a 16-bit address? So to address that problem, we say here that we have divided our memory into logical segment. We have divided into 4 logical segments. Each segment is 64 kilobytes in size. Now see, you have got 4 segments. Each segment is 64 kilobyte in size. Now, if you have any information within that particular segment, so you can access that information with the help of a 16-bit address. So with this concept, I can access around 256 KB memory out of 1 MB memory. So the problem is resolved up to an extent, but not completely. So we said that we have divided this 1 MB memory into 4 segments, into 4 chunks, and if I have any piece of information within that particular segment, I can access it with the help of a 16-bit register, with the help of a 16-bit content. So the 16-bit contents which gives us the starting address or the base address of that particular piece, of that particular segment, we call it as a segment address, or the segment, the contents are stored in a register, we call it as a segment register. So to address a specific memory location within a segment, now we need an offset address. So that offset address is also 16-bit wide, and it can be provided by one of the associated pointer or index register. Now what is this offset address? See, if I want to access particular location, for example, I want to access 8th row, and if I am standing in the front and counting from front the 8th row, so the number of bits needed to access 8th row is 3. So to access 8, you need 3 bits. Now if I am if I am standing in the middle, and now I am from the middle, I am counting the row, so I can say that from center 3rd row. So the number of bits I require to access that 3rd row, the 3, it's 2. So the bits have been reduced. The same concept we are using here. We say that you, within that segment, you have got the information, you can access it with 16-bit address. Now if you have something beyond that segment, or it may be the segment, the address just above the segment, so what you can do, you can say that I have the topmost address of that particular segment in my register plus 1, because I have to go to the next location. So that plus 1, that we call it as a offset. We call it as a relative addressing. Now with reference to some to the segment address, I have counted my offset. So now I have added plus 1, you can add plus 2, plus 3, but till how much number I can add? So you can add up to 16-bit number. So again, that means a 16-bit segment needs a 16-bit offset address. Now this 16-bit segment and a 16-bit offset, they generate a 20-bit physical address. So the memory segmentation is like this. I have got a memory. So we have got this memory which is 1 MB in size. This is my 1 MB memory. In this 1 MB memory, I have made 4 segments: code segment, stack segment, data segment, and extra segment. Now the size of each segment is 64 KB. Each segment is 64 KB. So if I have got any information which is stored in this particular segment, I can access it with the help of a 16-bit address which is being stored in the corresponding segment register. So I've got 4 segments: code segment, stack segment, data segment, extra segment. All these segments, they are having a corresponding register. So extra segment is having an extra segment register, data segment is having data segment register, stack segment is having stack segment register, and code segment is having code segment register. These segment registers, they are defining the starting address or the base address of that particular segment. So till this we know that up to 16, if with the help of a 16-bit content, I can access information within these shaded regions. But if I have something which I want to access from this region which is not shaded, like if I want to access something from here, what I can do? Now, if I have this topmost address in my segment register and I want to go beyond it, I can say extra segment plus 1 if you want to go here, or you can say if you have something below this segment, you can say stack segment minus 1. Now this plus 1 minus 1, you can directly give them in as immediate values, or you can store them in a register, and the registers which are being used to store this offset value, they are pointer and index registers. So with code segment, instruction pointer is being used, SPBP stack pointer and base pointer are being used with the stack segment, SI source index register is being used with data segment, and DI destination index register is used with extra segment. Now rules for this memory segmentation. So all the 4 segments, we have got the 4 segments, the 4 segments can overlap for small programs. That means in minimum all 4 segments can start at address 0000H. You can have a different base address, but they all can start with the same address, starting address, that is 0000H. And the segment can begin or it can start at any address which is divisible by 16, because you need the size, that is it should be 64 KB. So the difference should be such that the segment it can start with any address which is divisible by 16. Now what are the advantages of this segmentation? So it allows the memory addressing capacity to be 1 megabyte, even though the address which is associated with the individual instruction is 16-bit. You have got a 16-bit segment register, you have got a 16-bit offset register. So that means with the help of a 16-bit address, I am being able to access 1 MB memory. And also it allows my instruction, code, data, stack and portion of my program to be more than 64 KB by using more than one code, data, stack and extra segment. So it facilitates that you can use more than one segment. Also it facilitates the use of separate areas for program, data and stack. Like in 8085 we have got a common memory, that common memory is being used for storing my program as well as data. So here you know that the code segment is a separate area and data segment is a separate area. So you can have the separate areas for storing your instructions as well as your data. Then it permits a program or its data to be put in different areas of memory each time the program is executed. That means the program can be relocated, which is very useful in multi-programming. So just you have to say that my code segment is at this particular address. You have to assign a different address to your segment and it will facilitate the relocation. It will just shift the entire set of program to a new location. Now we come to know this, that I have a 16-bit segment address, I have a 16-bit offset address, but how actually this 20-bit physical address is generated? So to access a specific location from any segment, we need a 20-bit physical address, and the 8086 generate this address using contents of the segment register which is having your base address and the offset register associated with it. So every segment register have a fixed offset or the pointer and index register corresponding to it. Now the code segment, it will hold the base address of the code segment. So code segment is having IP instruction pointer with it. So the instruction pointer holds the 16-bit address of the next code byte within the code segment. So I can say that CS and IP, the combination of this CS and IP, it acts as the program counter here. So code segment is the area where my program is being stored. Instruction pointer is telling you the address of the next code byte of the within the segment. So they both act as a program counter. So the value contained in IP, that is the instruction pointer, is referred to as an offset, and this value must be offset from the segment base address in CS to produce a 20-bit physical address. Now, how will generate actually the address? So the segment address must be stored in segment address in segment registers. Offset can be derived from a combination of your pointers, instructions, pointer and index registers. Now we'll take this example. I have got a segment register address and offset address. So if you have a address segment address, you just need to shift that address by 4 bits and add the offset address. You will get a 20-bit memory address. For example, in this particular example, the code segment is at address 348AH. IP is having 4214. So the contents of code segment, they are shifted by 4 bits by one place, by one digit. So when they are shifted towards the left, so all the digits are shifted, becomes 348A, and a 0 is padded. For that means if I talk in terms of bits, then 4 0 bits are being padded. Then add both the numbers and you will got a 20-bit address. Same way, the data segment, if the data segment was at 1, 2, 3, 4, so I have shifted the bits 1, 2, 3, 4 and padded a 0 here, then added the contents of offset and we will get a 20-bit physical address. So the registers which are being used for this purpose of generation address, we have got a stack pointer. This is the stack pointer, you can say as a SP. It is of 16 bits. It points to the topmost item of the stack or topmost location of the stack. If stack is empty, stack pointer will be by default it will be at location FFFEH. Its offset address relative to the stack segment. So stack pointer always holds the offset address for stack segment. Then next is the BP, base pointer. It is again of 16 bits. It's primarily used in accessing the parameters passed by the stack, and it is also used for holding the offset address for your stack segment. Then SI, it is the source index register. The size is again 16 bits and it is used in pointing pointer the addressing of the data and as a source in some string related operations. So if you have got a string, that means you have got 2 arrays, a source and a destination array. So for string operations, your data segment along with SI will act as the source and extra segment along with your DI will act as the destination. So DI is the another destination index register. It is again 16-bit and it can be used as a destination for string related operations. It is related to the extra segment. So SP, BP, they are used with stack pointer, stack segment, SI used with data segment, DI used with extra segment, and we have already discussed that IP instruction pointer is used with code segment which acts as the program counter. So the segment registers, so we have got the 4 segments: code segment, stack segment, data segment, extra segment. These are the 4 segment registers. Then with the help of this, you can get a 64, with the help of these segment registers, these are 16-bit registers. So with the help of these 16-bit contents, I can access any segment which is 64 kilobytes in size. So you can have a 64 kilobyte data segment, code segment, extra segment and a stack segment. And this is your memory, which is 1 MB. By this memory is 1 MB in size. So it starts with address 0, 0, 0, 0 and 0H, ends with address FFFFH. So the only rule is that the segment they must be less than or equal to 64 kilobytes in size, and all of them can start at an address that ends with 0, or I can say they must be at address which is divisible by 16. Now the terminology. So the segment registers, we have assumed some values here, and so if 0100 is a 16-bit content in the segment register DS, it indicates that 0100 is the base address for my data segment. So see, if I shift it by one position with offset 0, so 0100, it is being shifted by 4 bits. So I have got a vacant position. So 0 will be padded to this position. If you have got a offset 0, then you will add 0 and you will get address 0100. 0, 0, 0, which is this address. So the segment registers, they used to define the base address for that particular segment. Same way, if 0, if you have got B200 in this, then by shifting it, you can get a B2000 as the base address for your stack segment, extra segment, and code segment. Now, it till where you can have this segment, the segment the maximum is 16-bit, so you can get up to 64 KB. So the particular range of address, that should be from minimum my lower address to the higher address, the range is 64 KB. Now this is the example of code segment. So I have got a code segment which is having 0400 value. So if I shift it, it becomes 4000H, and when you will add it with this 0056, you will get the another address. So that means with the help of this CS and IP, I am being able to access this part of my segment. So just see, 0400 was in code segment register. We shifted it to the left, then padded 0, and then added the number. So I've got a 20-bit physical address. So the offset is nothing but the distance in bytes from start of a segment, and offset is given by IP. So code segment, it used to be associated with the instruction pointer. Then instructions are always fetched with using the CS register. Code segment is the place which is being used to hold your programs. So instructions are always fetched from code segment. And the physical address is also called as the absolute address. The address with the 20-bit address which we are generating from segment and an offset address, we call it as a physical address or the absolute address. Now next is the example of the stack segment. The same procedure we follow here also. So the only thing is that the stack pointer, it is the stack segment, it is being used either with stack pointer or your base pointer. The procedure is same. You will shift the contents of segment register by 4 bits, and you will pad 4 zeros in that position. Just add the offset address, you will get a 20-bit physical or the absolute address. And yes, the stack is being, how you can access the stack memory? You can access it with the help of push and pop instructions. Next is the data segment. So data segment, again the same thing. Data segment is DS, and you can use it with the SI. So the effective address, it will be dependent on DS and SI combination. The same procedure, you will just shift the bits and just add the numbers. Now how the memory is being organized in 8086. So 8086 is having 1 MB memory. I have got a size of 1 MB memory, and we say that 8086 is a 16-bit register. But at every location, at each location, the data is maximum of 8-bit. So at any location, you have got a data which is 8-bit in size. So why we are saying that it is 16-bit? So we say that the memory, the complete memory is divided into 2 parts. I have divided the memory in such a way that all the even addresses 0, 2, 4, 6, 8 and so on, starting from 0, 0, 0, 0, 0H to F, 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 EH. They are arranged in one side, and all the odd addresses, they are aligned at other side, that is starting from 0, 0, 0, 0, 1H to F, 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 H. So you can see all the even addresses are on this side, all the odd addresses are on this side. So this is my complete 1 MB memory, where it is divided into 2 banks. Each bank is 512 KB in size. So I hope you got it, that we have got a memory which is divided into 2 parts, an odd bank and an even bank. So all the even addresses, they are aligned in one way, in one side, and we call it as the even memory bank. All the odd addresses are aligned on the other side, we call it as a odd memory bank. So the 1 MB memory is divided into 2 parts, 2 banks, 512 KB each. We have got an odd bank and an even bank. Now if you want to access the 8-bit data, you can access it either from your odd memory bank or from the even memory bank. It depends on your data, where data is stored. And if I want to access any data from 8-bit data from even bank, that is possible. If I want to access any data from odd memory bank, that means I have to select some pins. So they say that this BHE, bus high enable, and A0, they plays a very important role in defining whether I have to access my odd memory bank or an even memory bank. So if your BHE, bus high enable pin, bus high enable, if it is 0, so that means the higher bus is activated. If higher bus is activated, that time you can access the data from your high order data bus D8 to D15. So in that particular time, the higher byte will be transferred, and on the higher bus. If you want to access 8-bit data from even bank, that time A0 is 0 and obviously B0, BHE is that time 1. So your even bank is selected and your low order database is enabled. So the data will flow on low order database. So in we says that if I have got a 8-bit data, I can access it either from the odd bank or the even bank. So BHE, for example, if BHE is 1, A0 is 0, that time you can access it from even bank. I say if this is 0, it is 1, I can access it from odd bank. And if both are 0, then what will happen? If both are 0, that means if both memories are selected, you have to access a word. So first the lower 8-bit data from even bank will be accessed, then the higher 8-bit data from your odd memory bank will be accessed. So the lower 8-bit data, it will be flowing on my lower 8-bit data bus D0 to D7, and my higher 8-bit data, it will be flowing on D8 to D15. So when both the memories are enabled, at that particular time, first you will access something from this address, then you will move to this particular address. If it is having 23, it is having 17. So see, in one instruction, I am accessing the complete 16-bit data, 1723. That's why we call it that 88 is the 16-bit processor, because two locations are placed side by side, and you can say that we have got a 16-bit data in one go. So first it will access the data from your even bank, then from the odd bank. And yes, if you have not enabled both the buses, both the banks, if you have not enabled anything, then you are not able to transfer anything. Then you are not able to access anything. So none of the data will be accessed. And both are, that means a word. So the memory organization is such a way that two memories 512 KB each, they are placed side by side. First memory bank is the even bank where all the even addresses reside. Another memory bank is your odd memory bank where all the odd addresses are being assigned. So if you want to transfer, for example, how can I write in the instruction? I write move AL, comma, any, for example, I take any odd address, 0, 1, 0, 0101H, okay. It is odd address. So 0101H, it may be somewhere here. It is having FF at this particular address. So AL will be having FF. So you can play, if you want to transfer the data, then you can transfer it from the odd bank. Now another instruction I can write move AL, comma, 1000H. So this time 1000H. 1000H is the address. So 1000 is the even address. So that means the data from even memory bank will be transferred. So maybe 1000 is somewhere here. You have got the data EE. So in that particular instruction, AL will be having EEL in that. Now the third type can be, if you have got the instruction move AX, comma, 1, 2, 3, 4, H. So you have placed the even address. So when I have written this, then the offset is 1, 2, 3, 4. It belongs to the even address. So first the data from 1, 2, 3, 4 from this memory. Suppose 1, 2, 3, 4 is here. This is the 1, 2, 3, 4 address. So first the data from this address, it will be transferred to the lower accumulator. data from this part, it will be transferred to my higher accumulator, that is AH. So in one instruction, the complete 16-bit data is being transferred. So net conclusion is this, that if you want to transfer a 16-bit data, the address should be necessarily from the even bank. It should not happen that you want to transfer 16-bit data and you are mentioning the address from the odd memory bank. So to access 16-bit data, the address necessarily should be 16 bits. And another thing is, when you are mentioning the address within the square brackets, it represents the offset address. With the help from offset address, you always need to generate a actual or the absolute or the physical address. So how can you generate the physical address? For all in these examples, how can I generate? I can just simply say that the data segment multiplied by 10 plus my offset will give you the absolute or the physical address. Or you can say that you have got a 1, 2, 3, 4, just shift it by 4 bits, it becomes 1, 2, 3, 4, 0. Or no, if you have got a segment with 1000, then it becomes 10,000 plus 1, 2, 3, 4. So it becomes 1, 1, 2, 3, 4, a 20-bit address from where you have to access the data. So even addresses are on the low half of the data bus, that is D0 to D7. Odd addresses are on the upper half of the data bus, that is D8 to D15. So we have already visualized it from there, that the odd even addresses are on my lower part of the data cycle bus, that is D0 to D7. Odd addresses are on upper half, that is D8 to D15. And A0 is 0. So whenever A0 is 0, at that time data is on the lower part of my data bus, that is D0 to D7. Whenever BH is an active low signal. So whenever BH is activated, so the data is on my upper half of data bus. So if both are enabled, that means you are accessing a data, you are accessing a word. First, you are transferring a 8-bit data from the even address, then you are transferring the 8-bit data on the odd address. And that says that first the 8-bit data will flow on the lower order data bus, that is D0 to D7. Then your higher 8-bit data will flow on higher bus, that is D8 to D15. And obviously, we in general also, we used to read in this manner also, only if you have got a data. So first you will read this lower bits in the lower register, maybe BL, then you will read this values in higher register, that is BH. So in general also we used to do the same. So this was about the memory organization. So in net conclusion, I can say that the 86 is a 16-bit processor which with a 20-bit data address bus. It can access memory up to 1 MB. So to access that 1 MB memory, you need a 20-bit address. To store that 20-bit address, you need a 20-bit register. But 86, it doesn't have any 20-bit register. So to address that problem, we said that the memory is, we have got a concept of segmented memory. So the memory is being divided into pieces. Each piece 64 kilobytes in size. So if you want to access any piece of information from that particular chunk, you can access it with the help of a 16-bit register, with the help of a 16-bit address. So every segment is a 64 KB segment. So that particular segment is having a corresponding register to it, with the which is 16-bit, and you can access it. Then with the combination of 16-bit segment and 16-bit offset, you can generate 20-bit physical address. So in this manner, we can access the information. These are the references. So DV Halls are being used for and BV Bray, they are being used popular books for 8086. You can read from that. If you've got any doubt, you can contact me. Thank you.